In this video, we will be talking about gas laws. So, the first thing you need to know are the laws of thermodynamics. So, the first law states that energy cannot be created nor destroyed. Second law is the universe is constantly increasing the dispersal of matter and energy, which we'll talk about later, is usually why delta S is positive. And the third law states that the entropy of a perfect crystal at 0K is 0, although absolute zero cannot be achieved in a laboratory setting yet, so this has never happened, but it's assumed this to be true. So, reaction energy curves, these kind of show up a lot. So, the height of the yellow block over here represents the reaction's activation energy. So that means that the energy of the reactants are here, and in order for the reaction to take place, the energy needs to be added to the system and to achieve this peak over here. So the height of the blue block represents the energy released into the atmosphere after the reaction has taken place, otherwise known as delta H, which means this reaction would be exothermic because there's more energy at the end of the reaction than at the beginning, so that there is some energy released into the atmosphere. And if the reaction were to be flipped to products yielding reactants, then the sign of delta H would change signs. So some equations that are important to know are delta H, delta S, and delta G. And these are the same, just it would be the sum of the products minus the sum of the reactants, which will give you these values. And then this equation here helps you determine any of the, if you're given two, let's say you're given delta H and delta S and T, then you can solve for delta G. So if the system's at equilibrium, then delta G is equal to 0. So T must be converted to Kelvin, don't forget that. So delta H is enthalpy, which means heat change. So it's either exo or endothermic. So a positive delta H would mean the reaction's endothermic, so there's heat absorbed in order for the reaction to take place. If there's a negative delta H, that means it's exothermic, so there's heat released into the atmosphere after the reaction has taken place. So delta S is entropy. This talks about the second law of thermodynamics, where the dispersal of matter is always trying to increase. So it's usually a positive delta S, but in some cases there's a negative delta S, which means there would be increased disorder if it's positive and decreased disorder if it is negative. So Gibbs free energy is determining whether or not a reaction is thermodynamically favored or spontaneous. So positive delta G means that the reaction is thermodynamically unfavorable, so it is not spontaneous. But that does not mean that the reaction cannot take place. And a negative delta G means it's thermodynamically favorable, so it is spontaneous. Here's a helpful table. I used this a lot when I took chem last year, so if you want to pause and screenshot it, that would be really helpful for you to have. So this table is derived by delta G equals delta H minus T delta S, which shows that essentially when it would be a negative delta H, if it was at all temperatures, it would be negative minus a negative. So then it would therefore be a negative delta G, which means it's thermodynamically favorable at all temperatures. So basically this table is just derived from the equation, unless you want to think that out on your own on a test. So some common misconceptions about delta G is if delta G is positive, therefore it's not thermodynamically favorable, as we went over before, the reaction can still occur. So the reaction can be triggered by heat or another reaction catalyst, but there's no assuming that it's not going to occur at all. So also delta G has nothing to do with rate. If you have a really large negative delta G, which means the reaction's very spontaneous, it does not mean that the reaction is going to proceed at a really fast rate. So rate's a whole separate concept. So the kinetic theory of gases, this is kind of something you just have to memorize. Gases are mostly open space. Gas molecules are in constant motion. The velocities are constantly changing. Collisions are elastic. There are no attractive forces that would cause molecules to stick to one another. And gas pressure is caused by collisions of molecules in the walls of the container. So this is Graham's law. It's just basically a simple math problem. You have M2 and M1 are the molar masses, and the temperature and pressure must be kept constant if you're going to solve for the kinetic theory, the rates of these particles moving. So this is a little diagram to show the difference between diffusion and effusion. So diffusion, movement of gases from high concentration to low concentration. So essentially the pressure would decrease in this case if temperature is kept constant because volume is changing. So when the volume is increased, then that means that it's going to have less pressure, but it is the partition, it's essentially being moved from a different volume to a different volume. And effusion is, in this case, you can see there's a little hole in this partition. So effusion is the movement of gases from high pressure to low pressure. So here, these gases are slowly moving through this hole into the other side of the box, which is making the pressure lower because there are less moles of gases. That's all. I hope this helped. Thank you.